Hello, everyone. So I just got a text from Professor Darden a few minutes ago. He's on his way home from an eye exam at Kellogg Eye Center, so he should be on and answering questions in the chat in a few minutes. Hopefully he didn't get his eyes dilated. If he had, he probably wouldn't have been able to send a text very easily, so he should be able to read the chat. Okay, we're going to do Lecture 8 today, Heaps and Heapsort, and the first big part of this is about heaps and binary heaps. And this is important to you. Why? Because of Project 2, Part B, the binary PQ. So the heap sort is not important for that, but it's important in general. All right, so let's get into today's slides. So we're going to do a little bit of review of trees because the binary heap is going to depend on our knowledge of trees. So when we have a tree, we've got basically a graph with, we've got a graph that is connected and it has no cycles. Now we could give a second definition of that. We could say it's a graph where any two nodes are connected by a unique shortest path. Those two definitions are equivalent. So we could use either one. The directed graph, we're going to have relationships from the parents to the children. Really, we're going to want to be able to identify relationships in both directions. We want to be able to know who's your left child, who's your right child, who's your parent. We want to be able to do all of those. And we're going to use a binary tree where every node has at most two children. So the root is this topmost node in the tree. A parent is the predecessor of a node. A child is a node where this node is the parent, so further down in the tree along a path. And also an ancestor or a descendant. An ancestor is a parent of a parent, someone closer to the root following a path upwards. Just because it's closer to the root doesn't mean it's an ancestor. So for instance, in here, C is not an ancestor of H. It's higher in the tree, but it's not on a path between H and the root. Descendant is a child of a child of a child, etc., further down from the root following path. And then the leaf nodes are the nodes that don't have children. The internal nodes are the nodes that do have children. The root node is usually an internal node, but it could be a leaf node. If we just had a tree with a root and nothing else, it would be a leaf node for the root. Now we can create a structure to contain a node, and here I did it as a template. We'll get rid of the template in a few slides just to make things simpler. But we could put some sort of data inside of each node, and we'd have pointers to the left and right children, and this would allow us to go downward, down the tree from parent to child. If we wanted to go up the tree, we would need parent pointers also. So we'd need a third pointer for the parent. And that gets into a lot of memory involved in pointers. Especially think of it if we had a parent pointer because we needed it and the item was a character. Then we would have 24 bytes of parent pointers and child pointers for every 1 byte of data. Our tree would be 96% pointers and 4% data in terms of the memory that it occupies. So that would be kind of inefficient. Now, we got a few more definitions before we make things more efficient. So a subtree is just as much a tree as the original tree. A subtree, if I told you, hey, here's a pointer to 6, and that's all I gave you. Well, looking downward, everything that is a descendant of 6 is in the tree of which 6 is a root, or I should say the subtree, of which 6 is the root. So 6, 7, 1, 4, 3 are all a subtree. If I gave you a pointer to node 0, well, that's a subtree. It's the subtree rooted at 0. It contains one node and no more descendants from it. That's still a subtree. And if I gave you a pointer to 2, that would be a subtree that just happens to be the whole tree. Now, we're also going to need a few more definitions, and these are going to seem a little bit odd in how we index these, but it's important to be consistent, and we're going to use it later when we do self-balancing binary trees after the midterm. So we've got the height of an empty tree is 0. That would be the same as saying the height of a null pointer. If I give you a null pointer, you would say, the height is 0. It says, otherwise, the height of any node is the maximum of the height of its left child and the height of its right child plus 1. So the plus 1 is for the current node. So let's say I asked you, I give you a pointer to h, and I say, what's the height of the tree rooted at h? You would say, well, I take the maximum of the left and right. Well, the left and right are both null pointers. So the height of the left would be 0, height of the right is 0. Max of 0 and 0 is 0. We add 1 to that, and we've got a height of 1. And so the size is a simple one. Size of a tree, size of a null pointer is 0. Size of any node is the size of the left child plus the size of the right child plus 1. So we don't need a max here. We just take the 2 and add them together to get the count of the number of nodes in this tree. For the depth of an empty tree or the depth of a null pointer is 0. Anybody else's depth is the depth of its parent plus 1. So you can think of these as the depth is really how many pointers did I take to get to this node starting at the top. So let's do, for example, the root. If I gave you a pointer to the root and I said, what is the depth of this? You'd say, well, this is not an empty node, so we use the recursive definition. Its parent, it doesn't have a parent, it's the root. That's a null pointer. So the depth of its non-existent parent is 0, plus 1 for the root. The root is at a depth of 1. And the depth of a tree is really easy to label because assuming it's drawn nicely, is we can just go across in layers. A is at a depth of 1, B and C are a depth of 2, etc. Okay, I thought there was another slide after this one. Let's just do a few examples here together. So like I said, if we look at let's say the depth of the tree, or the depth of the nodes in the tree, we'd say this is a depth of 1, 2, 3, and 4. That's really easy. All right, if we ask for the height of the nodes, we'd have to label each one separately. We can't just label their categories along the side. So the easy ones are the children. We already did, leaf nodes. We already did h, the leaf node h. We said h was a height of 1. Well, then g should be a height of 1. So should E and I and F are all a height of 1. Think of it as how many pointers did you have to follow going down before you got to a null pointer? So I had to follow one level of pointers going down, and then I found a null pointer. So I had to follow one level to find a null pointer. Just like when I was searching for the depth of the root, I had to follow one pointer going upwards before I reached a null pointer. So once we've got all the leaf nodes labeled, well, then everything else is just the maximum of its children and add 1. So D would be the max of 1 and 1, plus 1 is 2. B would be the max of 2 and 1, which is 2, and add 1. So B is at a height of, B is at a height of 3. C, maximum of its children, 1 and 1 is 1, plus 1 for C. C is at a height of 2. And then A is the max of its children. 3 and 2, max is 3. Add 1, A is at a height of 4. And the maximum height that we see should be the same as the maximum depth that we see. We're just looking at it from different directions. Okay, so some fundamentals about heaps. So heaps, what we're going to do is we're going to build up this idea of a binary heap. But to get there and to do it efficiently, we're going to have to add some properties. So the first property we're going to add is the complete property. So remember, we're talking about binary trees in general, and in a complete binary tree, every level, except possibly the last, is completely filled, and the nodes in each level are as far left as possible. You could think of it another way. You could think of it as when I create one, I fill it from top to bottom, and when I go to a new level, I fill it from left to right, and I have to fill that level before I move down to a new level, or move to a new set of nodes at that level of the tree. So we can see the first one there is complete. It follows the rules. Every level except possibly the last is full, and in any level, in the only level that's not full, all of the nodes are as far left as possible. The middle one, it says the middle one's not complete because we've got two different levels. This level has things missing, and this level has things missing. So that broke the rules about possibly the last. So every level is filled except possibly the last. And we say possibly the last because if we look back at our complete binary tree in the leftmost, if H and G didn't exist, then every level would be completely filled. But if there are nodes in the last level is the one that's has the possibility of not being completely filled. Okay, so then the middle one is not complete because there's a gap in the depth of 3 level, and then in the last one it says it's not complete. It looks pretty crowded. The depth of 1 is fine, depth of 2 is fine, depth of 3 is fine, but at the last level the nodes are not as far left as possible because D is missing a right child. So if D is missing a right child, it can't be complete. So this complete property is going to be important for efficiency. And the nice thing about a complete binary tree is that we can fit it into an array without having any gaps. So if, for instance, if we allowed gaps, I could have a root node. I could have A has a child B, has a child C, has a child D, etc. And look at how many empty places I need in an array representation. I've got 1 at this level, 1, 2, 3 at this level, 1, 2, 3, 4, 5, 6, 7 at that level. I've got basically 2 to the nth empty spots in my array on the order of 2 to the nth empty spots. So that would be really wasteful, and we'd have to have a huge array to represent it. We would have to have a way to represent, hey, this node doesn't actually have data, it's empty, and it would make things really complicated, unnecessarily so. So what we're going to do is we're going to impose this rule of completeness. And once we impose the completeness rule, then we can put things in an array very efficiently. Now we showed here an array representation starting at 1. And this makes the math really easy, and it also leaves you something to do for binary PQ for Project 2 Part B. Is one of the things you have to accomplish in the binary PQ is taking the slides that we gave you with their 1-based representation and putting it into an actual vector that has a 0-based indexing. And the project spec has 3 different ways to do that. Okay, so we've got the completeness property means we've got no gaps in our tree, and when we want to achieve 1-based indexing with a 0-index vector, one of the things we could do is we could add a dummy element at position 0. So I could say, hey, index 0 over here exists, but I just put some default value in it and I don't ever look at it. And then when I look at my vector says the size is 10, but when someone asks me how big is your binary heap, I say 9. I lie a little bit. And if the vector size was 1 and someone asked me if it was empty, I would say yeah, because there's a dummy element I'm not letting you look at. So that's one of the 3 ways to do it. Another easy way to do it is when someone wants to say something like data sub k, we could instead write a function get element of k, which actually looks at, and let's assume that this is a real zero-based indexing and that x is there, the letter x. When they say get element of like 5, what we show them is data sub 4. So they say, show me element 5. We say, okay, you want to see element 5? I show you what's in index 4, because that's element 5 in a one-based indexing world. So we gave you those get element functions. There's 2 of them, one that's const, one that's not const. So it'll always work no matter what you're doing. So that's a second way. The third way would be to take everything in the slides and take the code and translate it to from one-based indexing to 0. That's the hardest. It's easy to get invalid heaps in that. It's possible to get seg faults with that. I know because I did both when I did this. So I've implemented the binary PQ all 3 ways. And I think the get element is the easiest because we gave you most of the code for it. You just have to we gave you all of the code to make it happen. You just have to substitute in. Wherever the slides say data square brackets k, you replace it with a call to get element parentheses k. So that's pretty easy to do. Okay, so when we've got our complete binary tree stored in an array, suppose I gave you an index I, right? I give you an index I, and I want to know what is the index of its parent, its left child, its right child, and whether that index represents a leaf node. Now, to accomplish the last one, we need one more thing than I. We have to know how big our binary tree is, our complete binary tree. So if we had something like dot size, we can finish number 4. So what I want you to do is take a few minutes, think about this. I'm going to mute my video for a second. Take a few minutes, think about this, and we'll come back. And remember, you can type things in the chat. I'm keeping an eye on it just in case anything happens before Professor Darden gets home from the eye doctor. Okay, so we want to know where is your parent. So let's do an example. If I gave you, say, I was 4, its parent is at 2. If I gave you 2, its parent is at 1. Those are easy. They're even numbers. What about 7? 7's parent is at 3. So it looks like we have Professor Darden joining us now. Okay, so if we've got just I divided by 2, and we assume we're doing real programming here in C++, we got integer division, I divided by 2 takes care of the even ones and the odd ones all at the same time. Whoops, I had a little glitch in my status. Looks like I glitched for just a second there. All right, it seems to be back. All right, so the index of its left child. So if I give you an index like 3, where's its left child 6? So, and if I said 2, you'd say 4, 4, you'd say 8. Looks like 2 times I. All right, what about the right child? All right, 2 times I plus 1. And we count on our precedence rules to give us the correct number there and do the multiplication first. Now, if a node isn't a leaf node, it must at least have a left child. It might have a right child, it might not. But to even get that far, we need to know, hey, is it even valid to ask about any children? If I give you an index I, does I represent a leaf node? Okay, well, let's do some examples. So 5 is not, and what is dot size here? Dot size is 9. Okay, so size is 9. So 5 is a leaf node, 5 is a leaf node, 6, 7, 8, 9 is a leaf node. Okay, so 5, 6, 7, 8, 9, those are all leaf nodes. We've got about half of our nodes are leaf nodes, and about half of them are not. Okay, well, let's look at that 9. If we say that about half of them are leaf nodes, let's take that size divided by 2. Size divided by 2 is 4. And everybody greater than that is a leaf node. Okay, that works at least when size is odd. What about if size was even? What about if G didn't exist and the size was 8? So no G, the size would be 8. And so 8 divided by 2 is 4. And the leaf nodes are 5, 6, 7, 8. They're still the nodes that are whose index is greater than size divided by 2. So if I is greater than size over 2, then it must be a leaf node. So that's going to be important later on. We're going to have to be able to tell if someone's a leaf node or not. All right, so we got those. So now what we've got to do is, besides the completeness property, we're going to add one more property to make it a heap. And that's the heap ordering property. So the heap ordering property says, and this is a max heap, so a tree is max heap ordered if every node's priority is not greater than its parent. So if every node has a priority that is not greater than its parent, it is a heap. And I think the word max here is out of place because it's always priority. Priority is always what's important. So whether it's biggest value or smallest value makes it a max or a min heap, but the highest priority is what's important. So the highest priority is the root, and no one can have a higher priority than their parent. So we apply this rule to every node in the tree. No node is allowed to have a priority higher than its parent. Now what if I said highest value is the highest priority? That would be a max heap, and that's what we have represented here. In the heap that we have here, it is a binary tree, it's complete, and the heap ordering property holds at every node. No node has a higher priority than its parent. Now we could, if we did this differently, we could make it a min heap where lowest value is highest priority, and then we'd have like the root of the tree would have to be 1. But still, no one would have a higher priority than their parent, higher priority meaning lower value. All right, and so we're going to add all these properties. We've got a binary tree, it's got to be complete, so we've got an efficient way to store it in an array, and it's got to have the heap ordering property, and that's applied at every node. And this is, think of it in terms of 280, this is in place of the rule about like small things go to the left and big things go to the right. Here, that rule doesn't exist. The rule is nobody can have a higher priority than their parent. They could be the same priority, like this 1 over here, this could be a 14. It doesn't have a higher priority than its parent. It has the same priority as its parent. and that would be fine also. All right, let's move it. Oops, wants me to draw with my finger. There we go. All right, so what we're going to do is we're going to look at a heap. We're going to, like I said, we're going to apply these properties, and what we're going to do with these heaps, once we have a binary heap and know how to create one and maintain it and keep it consistent at all times, is we're going to use heaps to make a priority queue, and we're going to use heaps to produce an efficient sorting algorithm. And the second one, the sorting, is going to depend on the first one. The first part, which is, like I said, the bulk of the slides, are the binary heaps and the priority queue. Your Project 2 Part B, binary PQ, has nothing to do with sorting, but it's the right day to give you Heapsort. Okay, so this basic idea is we want a data structure. We want a data structure that gives us access to the most extreme element, the highest priority. So when we say most extreme element, that's the same as saying highest priority. So it's always going to be the highest priority at the top, but if the largest value is the highest priority, that's a max heap. Smallest value is the highest priority, that's a min heap. And min heap and max heap are just shorthand names for referring to these, because it's a lot easier to say max heap than it is to say a heap in which the highest value is considered the highest priority. That's a lot of words. We say max heap instead. So what we're going to do is we're going to use an array representation or a tree representation. Using one of those, we can make a heap. Using heap, we can make priority queues. We can also make Heapsort. And we're going to go with the array representation here, because then we don't have to waste memory on pointers, and it's going to be really, really easy to build. Okay, so we've got to work on, before we get to how did this heap become a heap, let's look at maintaining it. What if I were to change something within it? So we're going to get to pushing and popping after we have some more basic tools, right? So I've got some very basic tools we need to build up. What if I said I change the key at heap of 8 and I increase its priority from 2 to 35? So that element down in index 8 is going to have its value changed, which is also going to change its priority. Right, so if we change its priority, then we have to be able to maintain the heap. So there we've got an animated slides here. So that 2 became a 35. All right, now we've broken that heap ordering property. And if we've broken the heap ordering property, then we have to fix it. So to fix this, what we're going to have to do is what? Well, 35 is out of place because it's a higher priority than its parent. So a simple thing to do would be to swap it with its parent, and then it would be in the right spot. Right? If it's higher priority than its parent, let's just swap it with its parent. So they swap places, and now we're back to a, no, we're not. We're not back to a heap yet because 35 is out of order with its parent, so we repeat the process. We swap 35 with its parent. And we keep doing that forever. No, not forever, until we get to a node where it no longer has a higher priority than its parent. So now 35 is not a higher priority than its parent. We have restored the heap property, and it's a heap again. Now in the bottom, we've got the array representation. So I just did that really quickly. So we got the array representation. When we draw the tree, it's easy to see what's happening because it's easy to see who's your parent, who's your child. But really behind the scenes, when we write the code, we're going to write the code to do an array representation. So in the array representation, 2 becomes 35. Well, 8's parent must be at index 4, so we check, hey, 35, are you higher priority than your parent 9? Yes, you are, so let's swap those. Let's swap 35 and 9. Whoops, I didn't know exactly when the animation stopped. Okay, so we swap 35 and 9, then we compare 35 at index 4 to its parent at index 2, higher priority than its parent, so we swap it, and this one's sort of showing we put 35 in temp, we copy 18 over to 4, and then we copy 35 from temp over to index 2. And then we check 35, index 2 compared to your parent. You're not a higher priority than your parent, so we have finished fixing the priority. And so what we've got here is we've got a function called fixUp. FixUp is named that way for two reasons. One reason is that the priority of an item got increased. If the priority of an item got increased, we need to fix from the bottom towards the top. And so that's why it's called fixUp for two reasons. One is that a priority changed. Two is that as we fix it, we're going to be going up the tree to do the fix. So let's look at the code here. So the code is saying, hey, you gave me an array of items and an integer k. K is the index whose node's priority has changed. So k is the index of the changed value. Now, if k is the index of the changed value, what I've got to say is, hey, I've got to keep going. I've got to keep fixing things as long as, okay, so what does the while loop say? It says, keep going while k is greater than 1. Okay, well, what is index 1? Index 1, let's look at back to the previous slide. Index 1 would be the root. Aha. So while k is greater than 1 is the same as saying while you are not at the root. Okay, so while you are not at the root and heap square brackets k divided by 2 is less than heap of k. Okay, so if my index is k and I'm not the root, then who is k divided by 2 would be my parent going upward. Okay, and the order here is important because Boolean short-circuiting. If k is 0, or sorry, if k is 1 and k is the root, the k greater than 1 fails. We've got false and anything, and the second part never gets evaluated. And that's important because if the second part were to get evaluated when k is 1, we would look in heap sub 0, and index 0 doesn't exist in the 1 based indexing. Okay, so that's important. So the ordering is important here. So while I'm not at the root and my parent, my parent's value has a lower priority than my value. So as long as I'm not at the root and my parent's value is lower priority than mine, I should swap my value with my parent's value, and swap comes from the STL, and then I should move up. K divide equals 2 is the same as saying k equals k divided by 2, just shorthand. So we say move up a level, move to your parent, and remember k was an integer, an index passed in by value. So if we modify k, we've got a copy. Someone else had an index in mind. We got a copy of the index. We modify our copy. We're not modifying someone else's value. Okay, so we move up to the parent, and we keep doing this. As long as we're not at the root and your parent has a lower priority than you should swap them. Now this code has one thing that I said out loud wrong in that it's an interpretation. Here, when we say less than you, so your parent has a value less than you, I was saying priority. But really the way this is coded is it's kind of hard-coded for assuming high value is high priority. So if your parent has a lower value than you, then it must have had a lower priority than you. And this is where functors come into play. In your project, you're not going to be able to write the code this way. You're not going to be able to say less than with values inside the data structure. You're going to have to use a functor. You're going to have to call the functor and ask it, hey, I've given you two things, A and B. Is the priority of A less than the priority of B? If you say yes, then I do it one way, and if you say false, I do it a different way. So that's one of the other translations you have to make in the code, is that you're not going to be doing less than and greater than on data directly. See here, we're doing less than or greater than on an index. That's fine, we're dealing with integers. But in the project, you don't know that the heap contains integers. You don't know that it wants to be a max heap. So instead of doing less than and greater than on data values, you call the functor. The other thing you'll have to deal with is that your fix-up is not going to be a standalone function that receives an array and an index. It's going to be a member function that just needs to be given an index, because there is no array. There's a vector. There's going to be a vector inside that's a member function. So that's the other thing you're going to have to do to translate it, the slides into the code for the binary PQ. Okay, so this is all fix-up. This is if a value increases in priority, we fix upwards towards the root. All right, what if a value decreases in priority? All right, so it says, what if we reduce the key at heap sub 2, so at index 2, changed from 18 and it became a 3. So it got reduced in priority. Well, with respect to its parent, it's still fine. And I sort of glossed over that when we did the increase in priority. Let's just go back there for a second. When we increase priority and we say, hey, that 2 became a 35, it's fine with respect to its children. Well, first of all, it's a leaf, it didn't have children. But if, let's say, 9 had become a 35, if 9 becomes 35, it's still fine with respect to its children. It was already of a priority not less than its children. If the priority went up, it's still a valid parent of those children. Okay, so now let's go back to decreasing priority. So if index 2 changes from 18 to 3, it has decreased in priority. With respect to its parent, it's fine. But with respect to its children, it might not be fine. In fact, we've broken the heap ordering property. So when we fixed up, we said if you're a higher priority than your parent, swap with your parent. Here, we've got to say if you're a lower priority than your children, swap with your children? I can't swap with both of them. Should I swap with the left one or the right one? Well, I'm less than my left child, so I should always swap with my left? Not necessarily. If I were to always swap left or always swap right, I might swap with the wrong child. I might swap with 7 and end up with 7 being the parent of 9, and I've just changed the problem, changed the incorrect heap ordering. So we always have to swap with not the left, not the right. We've got to swap with the highest priority child. So if we are a lower priority than either of our children, we swap with the higher priority of our children. Okay, so the 9 and the 3 swap. Oh, that was the bounce there. I haven't done the animated slides of these. I didn't realize the bounce was in there. Okay, so we take the larger child and we swap it with the parent. Okay, now 3. Have we restored the heap property? 3 with respect to its left child is fine, but with respect to its right child, it's not. So we've got to say, hey, 3 with respect to 4. So the heap property is not restored. So take your largest child, swap with your largest child. And now we've reached a leaf level. We've reached a leaf node. If we're at a leaf node, this has got to be in the right place because it doesn't have any children. It can't be out of order with respect to its children. So when a node decreases in priority, we have to fix going down until either the heap property is restored or we reach the level of a leaf. And in the array representation down at the bottom, so the 18 became a 3, we check its children, 9 and 7, take the bigger one and swap with it, and then we've got, hey, 3, your children, or index 4, I should say, index 4, your children are at 8 and 9. Are you a lower priority than any child? Yes, you are. 4, so swap with 4. And then you've reached a leaf level, so we're fine. So our code takes place on the array, but I find it a lot easier to get these right if I draw out the tree representation. And really what I tend to do is I don't do both like we did in the animated slide here. What I do is I do all my work on the tree representation. Like I just start, there's a big long animation. So I start here and say, hey, I've done everything I need to do on the tree, and then let's just cross out stuff in the array representation and say, hey, that's now a 9, and that's now a 3, and that's now a 4. So I just do the tree representation and then make the array representation match the tree is the easier way to do it, I find. Okay, so when the priority of an item is decreased, we need to fix down. So the value has gone down in priority, we need to fix moving down, and this one is a bit more complicated than the other one. So, first of all, the parameters. We receive the heap, we also receive k, the index. This is the same thing before, this is the index of the one that changed, but we also need to know the heap size to know if we're at a leaf node or not. Remember we had that formula that told us if we're at a leaf node? Okay, so that's our parameters. So now we've got a while loop again. While 2 times k is less than or equal to the heap size. So remember we said it's a leaf node. Leaf node, we would say it's a leaf node if k is greater than the size divided by 2. Well, what we need to know now is we want to know what if it's not a leaf node? Because if it's not a leaf node, we have to keep going. Now, I suppose we could have done that same comparison, threw my pen. We'd have to do the same comparison. We could put it in parentheses and put an exclamation point, a bang in front of it to negate the logical conclusion. But here we just redid the formula. So the formula to say it's not a leaf is 2 times, we basically took and multiplied both sides of that by 2. So is 2 times k less than or equal to the size. So we multiplied 2 by both sides and we reversed the comparison. Okay, so that's what line 2 is doing, is we're saying while we're not at a leaf node. Okay, while we're not at a leaf node, we know we have a left child. If we're not a leaf, we've got to have a left child. We might not have a right child, but if we're not a leaf, we've got to at least have a left child. So that's what line 3 is doing, is saying, hey, index j is the index of the left child. All right, now let's check out line 4. Line 4 says if j is less than heap size and heap sub j is less than heap sub j plus 1. Well, if j is the left child, then j plus 1 would have to be the right child. But what if the right child doesn't exist? That's what the first part is doing. This j less than heap size is saying if you have a right child. Because if j was equal to heap size, then it would be the only child. But if j is less than heap size, there must be a right child. So that's what that line is saying. So it's saying if there is a right child and the left child is less than the right child. So if both of those are true, if you have a right child and the left child is less than the right child, then increment j. So J, whether this if happens or not, J is the index of the highest priority child. That's what this line is trying to do, is we're saying in line 3, we said, I know I've got a left child, and I'm assuming the left child is the highest priority. Line 4 is saying, well, if you've got the right child and it's a higher priority than the left child, then the index of the child you need to swap with would be the right child. So after line 4, J is the index of the highest priority child. Now line 5 is a check. Hey, am I done? So if the parent has a priority greater than or equal to that of the highest child, the heap property is restored. So line 5 is asking, is the heap restored? If the parent has a priority greater than or equal to the child, the highest priority child, not just any child. So if the parent has a higher priority, a priority greater than or equal to the priority of the highest priority child, then we can break. We can stop this loop. Otherwise, the loop keeps going. And there's no else clause, we just keep going. So if we didn't break, the loop keeps going, and we swap the parent and the child, and we move down. We move down into the highest priority branch. Okay, so we move down into the branch with the highest priority. So we check if we've got children, we figure out who's the highest priority child. We check if the heap property is restored, we can break, we're done. And if not, if we didn't break, then we swap with the child, the highest priority child, and we move down into the branch of that highest priority child. And then we go back through the loop. So we can see this in the example here. Go back through it. Take some time. Go back through this and put them up side by side. Like load up your PDF, or maybe load the PDF twice, or print it or something like that, and print one page of it and look at it, or draw out the tree. Just draw out the original tree that we had here. Draw out the original tree we had here and go through the example with J, K, etc. Okay, so that's the code for the fix down. Now, when you implement this, again, this is going to become a member function, so it's not going to have to be given the heap. That's just going to be a member variable that's a vector. It's not going to be given the heap size, because if you've got a vector, you know the size of the vector, or you're a member function, right? Fix down is a member of the class. The class has a member function called .size. So the binary PQ has a member function called .size. So you don't need to be given the size, you know the size. Also, when you implement this, don't, and in fact there's a note in the starter files that says you're not allowed to create a member variable for the heap size. The autograder will in fact reject you if you create it. So you can't have a separate variable for the heap size. You need to use either data.size. Data is the name of the vector that we put in there as a member variable. You can either see data.size, or you can just say size. So you can just say size, parentheses, and it will call, because you're a member function, it calls your own member function size. So just in your code, you could say is J less than size, parentheses. And that calls the member function size, which does whatever it needs to do with the data.size. All right, so that's our code for fix down. Now those are basic tools. Now remember, we're going to use this to make a priority queue. So in a priority queue, people in the middle don't usually have their priorities changed. That would be kind of odd. What we really need is we need a push and a pop. But we're going to use these two basic tools of fix down to accomplish those tasks. So when we do a PQ, what we really need is a push and a pop. We need a top. We need a way to look at the highest priority element. And priority queues can be used for lots of different things. There's algorithms, shortest path, which is Dijkstra's algorithm. We can use it for minimum spanning trees. Priority queues can be used for lots of different things. And in fact, you're going to be discovering in Project 2 Part A all the different things that priority queues can be used for, right? We're using them for our stock market trading. We're using them to keep a fast running median. Oh, I gave that away. Watch the video. The video gives it away too. So we're going to use those in the fast running median and possibly other things in the project. Part A. Okay, so that's what we're going to do with them. So what we want to do is we want to push. Well, we've got this vector representation behind the scenes. So when I say priority queue push 100, really behind the scenes, it has to put it into the vector. So where's the most convenient things to add things to a vector? The back. That's why vectors have a function called push back. So we push back to the back of the vector, and whoops, I'm going to draw this myself. So we push back into the vector. We say, hey, add a new element out here with 100 in it. I push back to the vector, and really the tree is just a way to view what's happening with the vector. What happens in the tree is that 7 gets a new left child that it didn't have before. So index 10 gets the value 100. Now, we don't have a function to help us with newly appearing nodes, but 100 has a higher priority than its parent. But 7 didn't used to have children. Think of it this way. 7's left child, which didn't exist, had an infinitely low priority. It has gone from infinitely low priority to something higher than infinitely low. In effect, 7's left child has increased in priority. And if 7's left child has increased in priority, we must fix up. So, thing that used to be infinitely low priority now has a priority of 100. Is it out of order with respect to its parent? If it had become priority 1, we would be fine. We'd check the priority of the parent. We'd say, you're not a higher priority than your parent. You're done. We've fixed it. But because it's 100, we've got to compare it to its parent. It's a higher priority than its parent, so we swap them. Are you a higher priority than your parent? Yep, okay, we got to swap you. Are you a higher priority than your parent? Yes, we've got to swap you. And now the heap property has been restored. Now I got to erase my markings because the animated part of the slide with the array comes next. So behind the scenes in the array, we, whoops, don't want to draw with my finger, we push it at the back, and then we start restoring the property. So we check it with respect to its parent at index 5, swap it, check that with respect to its parent at index 2, and swap it, check it with respect to its index at parent 1, we swap it. Hey, we've reached the root level, we're done, our loop is over. So that's what's going on behind the scenes. So in the push here implementation, we've got a few things happening here. So we say heap square brackets plus plus heap size. Okay, wait, that's a pre-increment. So heap size gets incremented first. So we put it in heap sub plus plus heap size, set that equal to new item, and then we call fix up. Well, remember, when we implement this, we're not going to have a heap size. We're not going to have an array. We're going to have a vector. So this line is really easy. We just replace this whole thing with data dot pushback. Okay, so that's almost done. Then we call fix up. Oh, except fix up doesn't accept a heap size anymore because it's a member function that just, oh wait, it doesn't, sorry, mistake on that one. So this one becomes a pushback. It's not past the heap anymore, right? It doesn't get past the heap because the heap is the member variable, and it doesn't need to be given the heap size. We could give it to it. We could basically, we wouldn't give it heap size. We'd give it just size. So we can still give fixup the index to start at. That's how the code of fixup is written. It needs to be given something, the index to start at. We could give it size. So the code for the push is pretty easy. It's the fixup that's more complicated. So this one is easy to fix. We replace that line 2 with a pushback. We change line 3 a little bit, and we're all set. So pushing into the priority queue means we've got to add it to the underlying data vector, and we've got to fix up until it's back in the right place, until the heap property has been restored. And like I said, if we had pushed back 1 over here, we'd be done really quickly. We'd push back, we'd compare it to its parent, it'd be fine, the fix-up would finish after 1 test, and we'd be done. Okay, so that's priority queue insertion. We need priority queue deletion. So we've got to say pop. Okay, so we want to get rid of 81. So let's look at what happens here. Now, and we have to sort of consider the underlying vector. We don't want to pop front on the vector. Well, one reason is vector doesn't have a pop front. Reason number 2, it's not quick. So you could say, well, wait, let's just make it a deck and we'll just pop front on the deck and everything will be fine. Well, not really, because then 18 would become index 1, its children would be 14 and 9, and they would have odd children. It wouldn't necessarily restore the heap property. Also, what if we reverse these? What if this was 14 and this was 18? If I just make it a deck and pop front, I haven't fixed it, because the highest priority element is not necessarily the left one. So you're gonna ask a dozen questions in either the chat or in office hours about, well, what if we did this? What if we did that? They're all gonna involve more work than what we're really gonna do. So let's look at the right way to do this, and we'll be happy to answer your what if questions, but I can guarantee you they're not as efficient as this. So I want to get rid of 81. So let's think about the underlying vector. Where is the easiest place to get rid of something in a vector? It's at the back. So I would like to pop back on the vector, but that would get rid of 4, not 81. Aha! Let's replace 81 with the very last node in the tree. So let's replace that 81 with 4. Well, now we've got to do 2 things. First of all, we've got to get rid of that node down there. Whoops, sorry. I'm backwards. I thought the animated slide did it in one order. It does it in a different order. So we've got to fix down. So 4 is too low of a priority, so it swaps with its highest priority child. 4 is still in the wrong spot, swaps with its highest priority child. 4 is still in the wrong spot. Oh no, it's in the right spot because it's higher priority than its children, and we've got to do a pop back. I would have personally, Professor Darden did the cool animation. Personally, I would have popped first, because that's really what happens with the underlying vector. So we get rid of it we get rid of 81 by replacing it with the lowest, not the lowest priority value, the last value in the vector. In this case, it wasn't the lowest priority value. The lowest priority value would have been 1. And that would have produced problems, because then if I get rid of 1, I'm getting rid of something in the middle of a level. Remember, complete binary tree. The only thing we can get rid of is the rightmost in the bottommost level is the only one we can get rid of and still be complete. Which in code is easy because it's the dot back of the vector. So we replace the root with the dot back. And you're going to be tempted. When you write this in code, you're going to be tempted. You're going to say, set the root equal to data square brackets data dot size minus 1. Oh, and you're going to give me a headache right here if I see that. Don't write in your code, don't say data square brackets data dot size parenthesis minus 1. That's really, really hard to read. That is the same as data dot back. So much easier to read. faster to type. If you're taking an exam and you need it, hey, that would be the fastest way to type it during the exam. Or if we were in person writing it by hand with a pencil and paper, data.back is a lot faster than data square brackets, data.size parentheses -1 close square bracket. Okay. So, sorry, rant mode off. Okay, so we replace it with the last value in the vector and we fix down. And then the array representation, we do basically the same thing. We replace it with the 4, and then we pop back. We should get rid of that thing now. And then we fix down. We swap with the highest priority child until the heap property is restored. Okay. Yes, Professor Darden likes my rant because he hates saying data square brackets, data.size parentheses -1 close square bracket also. Okay, so when we delete, so the code here has one thing that's really important is we don't do a swap for our first step. Notice when we did this, I didn't swap 4 with 81, I replaced 81 with 4. A swap takes 3 changes to memory. To do a swap, I have to say temp equals A equals B equals temp. Well, that's too much work. I don't need 81 at the back of the vector when I pop back. I just want to replace it. I just want to say, hey, heap sub 1 equals heap sub heap size minus. Well, no, I'm not going to do that. I'm going to say data sub 0 equals data dot back. Or it could be data sub 1 equals data dot back. It all depends on whether you're doing a dummy element or not. If you're doing a dummy element, you would say data sub 1 equals data dot back. And this line of code is going to have to turn into 2 lines because you're going to replace what's in the root element and you've got to do a data dot pop back. Oh my gosh, we added a line of code. Okay, but important. So we replace that line with an assignment and a data dot pop back. And then we call fix down. Well, fix down, we don't have to give it the heap because that's a member. We don't have to give it the heap size. We just have to give it index 1. Index 1 is, we're saying fix down where? Starting at the root. So fix down, that 1 is k. This is our value k. K is the index who has changed. K is the index that we must do a fix down on. And here's a place where it's really important. The dot pop back has got to go before the fix down. If we don't pop back before the fix down, then we might fix too far, or we might make a mistake. It's just important. I would say it's important here. I'm confident the code will work correctly if we pop back before we call fix down. If we pop back after we call fix down, it might work, it might not. But I'm less convinced of it without more thinking. Yep, true. Data.front is the same as data sub 0, but if you're doing a dummy element for data 0, you would have to say data sub 1. Okay, now that we have done binary heaps, you can now understand a brand new XKCD. And that's the subtext at the bottom is the mouse over text from the XKCD. Aster, it all depends on how you'd write the code. If you rewrite everything in these slides to be 0-based indexing, then you would call fix down of 0. But if you use get element, you would call fix down of 1. So if you use get element, you would call fix down of 1. Your fix down thinks of things as 1-based indexing, you would call fix down of 1. The only way your only time to call fix down of 0 is if you change everything in fix down to accept a 0-based index of what to fix. So like I said, I think the simplest way to translate the slides into the binary PQ is to use get element. And if you're using get element, you want to say fix down of 1. Okay, so like I said, new XKCD that you can understand. I'm sure you're all just laughing uproariously at home. Anyway, here's our summary slide. We're not done yet. This is our summary slide of priority queues. So, priority queue, remember we talked about those back on lecture 2, was just this idea of insertion of an element, inspection of top priority item, and removal of the top priority item. And we've shown a couple different ways to do it. We gave you unordered PQ, and we also gave you unordered fast PQ. We gave you 2 different implementations of the unordered PQ. So the unordered PQ is O of 1 insertion. You just throw it at the end of the vector, but when you want to know where the top is, it takes O of n time to find it, because you got to look at everybody. If you want to remove the top item, it says that would be O of n or O of 1. That's the difference between unordered and unordered fast. And what unordered fast does, I'll give you the 30-second preview, because you almost always look at the top and then pop. When you're using priority queues, those operations tend to follow each other. You don't usually look at the top, push something, and then pop. You usually look at the top, pop the top, and then push something new. So because pop almost always follows top, if top were to remember where the highest priority element is in, say, a member variable, then pop could say, hey, if I know the best index, I use it. So that's how fast gets O of 1, removal of the top item, is that top remembered it. How did it remember it? Wait a minute. Top is a const member function. Const member functions can't change member variables unless that member variable is mutable. So unordered fast PQ uses a mutable member variable. Okay, so sorted PQ. Sorted PQ says insertion of an item is slow because it only takes us log n time to figure out where it should go, but to move everybody else in the vector over by 1 takes O of n time. So it's O of n to insert, O of 1 to respect, O of 1 to inspect, O of 1 to remove. Now if you think about the lifetime of an item, items get pushed into a PQ and then eventually they get popped. So they get pushed, later on they get popped. So that combination, each element gets pushed and popped. So between the push and the pop, between push and pop, it's always combined cost is O of n. So if we add them together, it's O of n to push it and later on to pop it. With a heap, oh my gosh, we didn't even talk about efficiency. We're going to have to go back and talk about efficiency. I forgot that. I haven't presented these slides in a while. In the fall and winter, I did the first 6 lectures and someone else did the next 6, etc. I haven't done these in a while. We totally skipped over complexity when we did those. Let's go back and talk about complexity. So what we need to do, I gave you the punchline here is log n. So let's go back to these. So I need to go back to fix up and fix down, right? When I fix up and fix down, we said, hey, we've got this element that changed priority. Get rid of my markings on here. We've got this item that changed priority. I must fix going up. Well, I've got to fix all the way from wherever I just changed all the way to the top. How far away is the top of the heap from me? Well, there's n nodes, right? There's n nodes in here. What's the height of the tree? The height of a complete binary tree is always on the order of log base 2 of n. I say on the order of because here there's 9 nodes. Well, 9 doesn't have an exact log. It's equal to the ceiling of the log base 2 of n. Or it could be the floor, but it's approximately the log. So here we had to fix, so I had to swap it. I had to swap with its parent, swap with its parent. Oh, but then I didn't have to go all the way to the root. That's why we want to say this is big O of log of n. because we could get lucky. You know, we could have changed that 2 into a 3, and I didn't have to fix all the way up. Its worst case is log of n. Its best case is O of 1. We could swap a value with a tiny thing that's small priority, and we don't have to fix all the way to the root. But at most, we'll have to fix all the way to the root, but the root is only log n away, O of log n away. Is it ceiling? Is it floor? Who cares? It's O of log n. That's the beauty of big O, is we don't have to know the exact ceiling, floor, whatever. So fixing up is log n. If we do the fix down is, hey, I've got a variable lowered priority. I have to fix at most all the way to the leaf. Well, all the way to the leaf is at most log of n away from wherever I am right now. And we could do the analysis on the code also. Oops, we got animations there. When we get to the code for fix up and fix down, oops, that's code's a little bit busy. Let's get rid of those. Oh, it doesn't want to. Oh, it won't let me erase the pen markings on this slide. There's just too many of them, or too old or something. It won't let me erase. But think about what we did. We started out at an index, and every time we go through the loop, we double that index. Or double that index and then later add 1. So our index, we started at index 1, we double it every time. It's at most log n times before we reach n if we double it every time. So fix up and fix down are log n. Well, that means that push and pop that depend on fix up and fix down, push and pop must be log n also. So we've got efficient log n push, we've got efficient log n pop, because our push and pop, our insertion and removal of new elements, push and pop depend on fix up and fix down, which are log n. So the heap, if we look at the combined pushing and popping, is O of log n. Doesn't quite fit in there very well. So it's O of log n. Pushes and pops combined are log n. So this is going to be faster than the unordered. It's going to be faster than the sorted. All right, now let's look at what else we can do with heaps. Is we can heap sort. All right, so let's say I started out with an empty vector. I could start with an empty vector and I keep pushing to the vector and then fix up. And I push and I fix up and I push and I fix up, push and I fix up. So I could do that, but that would be n log n time. So we're just talking, we're not talking about sorting, we're talking about producing a valid heap. Just if I give you a random collection of stuff, I give you a vector and I say, turn this random collection of stuff into a heap. Well, you would have to just push n at a time, and each complexity has a maximum, each push has maximum complexity of log n, would take us n log n time. And it would take us an extra vector, basically. What we could do instead, so we could also say, hey, I could take this and I could sort it in reverse order. Reverse order sorting would be a heap, right? If I had like 100 has children 50 and 60, or whoops, 60 and 50, and 60 has children 40 and 30, and 50 has children 20 and 10, right? This is in the underlying array would be 100, 60, 50, 40, 30, whoops, 30, 20, 10. If I reverse sort it, that is a heap, but sorting takes n log n. We don't want to do n log n time here. We want to get this down faster than n log n time. We'd like to turn a random collection of numbers into a heap faster than that. And the tools that we have are fix up and fix down. So we have fix up and fix down. We could proceed from bottom to top using either one, or we could proceed from top to bottom using either one. So that's 4 possibilities. I could use fix up or fix down. I could proceed from the bottom to the top or top to bottom. That's 4 possibilities. Of those 4 possibilities, 2 of them work and 2 of them don't. The 2 that work have different complexities. So here's the 4 possibilities. So, and this is saying, hey, I don't even need any extra memory. I could take the vector you've got and I could turn it into a heap in place inside that vector. I could proceed from bottom to top doing repeated fix downs. That one is O of n time. We're going to give you a hand wavy proof in a minute. It's O of n time, and that's what standard make heap in the STL does. Okay. We could go from bottom to top calling fix up. It produces an invalid heap. And what it says here is try this. So if I treated this as if it was already in a heap, like 5, 3, 6, 1, 2, 4, 7, so that I say let's treat that as a heap and let's call repeated fix ups from bottom to top, you'll see that you get an invalid heap at some point. Okay, I could proceed from top to bottom calling fix down. Here's an example. Draw it out, run through it. You'll see it comes out invalid. And the last one is I could go from top to bottom calling repeated fix ups. This one works, but it produces n log n complexity, which is the same complexity as fully sorting it. So that is not the right way to do it. So the right way to do it is go from bottom to top and call fix down. Now this heapify is actually needed for the project. We're not at Heapsort yet. We're just turning a random collection of stuff into a heap. Why is this needed for the project? Project 2, Part B, binary PQ, one of the things you have to implement is a range-based constructor. So I say basically, here's 2 iterators, inclusive, exclusive. Here's 2 iterators. Turn the random collection of stuff in this container into a heap. So that would be a way to do something like, hey, I've got a collection of data. I want to turn it into a heap, and then I can do like pushes, pops, fix downs, whatever. But you've got to accomplish it in O of n time. So to accomplish it in O of n time, you have to do this. Okay, so we're going to look at how this works, how the bottom up fix down works. And when I say bottom up, really behind the scenes, I mean highest index to lowest index. Now, we said we're going to call fix down on these. So I said, here's a random collection of numbers. So here's a bunch of numbers, same numbers we had before in a different order. We throw them we have them in this array or vector, and we treat it, we say, well, let's look at this as if it was in a heap, and let's call fix down on stuff. So we're going to call fix down from bottom to top, really from highest index to lowest index, but not quite all of them, because the leaf nodes can't fix down any further. The leaf nodes are already fixed. Really, I need to call fix down on everybody who's not a leaf node from highest index to lowest index. That's bottom to top. So I would call fix down on index 4, call fix down on index 3, index 2, index 1, and we'll be back to valid. So we've got the animated slide to show you here what happens. So I call fix down on index 1. We say, hey, 1, you're a lower priority than your children. I think your highest child should move up. All right, index 3, let's call fix down. 5, are you out of place with respect to any of your children? Yes, you are. Okay, highest priority children swaps with you. All right, index 2, value 2, same thing. Index 2, are you out of place with respect to your children? You are. So let's call fix down on index 2. But remember, the fix down's not done. Fix down has to go from index 2 all the way down to either restoring the heap property or reaching a leaf node. Heap property is not restored yet. We got to keep going down. So index 4, are you out of place with respect to any children? Yes, you are. Swap with the highest priority child. Index 8, are you out of place with respect to, oh wait, I've reached a leaf node, I'm done. All right, index 1, are you out of place with respect to either of your children? Yes, you are. Okay, swap with your highest priority element and continue fixing down. Fix down has to keep going, right? Index 2 to 4 is out of place, so we swap. Index 4 versus 8, 9 is not out of place. The heap property was restored before we reached the level of the children. We're done. This is now a heap. And behind the scenes, the same thing happens to the array. All of the leaf nodes are fine. They don't need to have fix down called on them. We call fix down on index 4, which swaps with its largest priority child, and the fix down is done. Call fix down on 3. Check 3 with respect to its children at 6 and 7. Swap with the highest priority child. We've reached the level of a leaf node. The fix down is done. Move over to index 2. Check your children at 3 and 4. Swap with the highest priority child. Fix down is happening. So we swap there, and then we keep going with the fix down. 4 and 8, 9. Are you out of place? Yes. So swap with the highest priority child. Oh, look, index 8, you're a leaf node. You are in the right place. The fix down is done. All right, index 1, fix down. Check with your children. Swap with the highest priority child. Index 2, check with your children. Swap with the highest priority child. Index 4, check with your children. You're okay with respect to your children. Fix down is done. All right, so we've restored the heap property in both views. Now, what we're going to do here is we're going to give a hand-wavy proof of complexity. So we're going to move that graph over. We've got this same graph from the last slide. The leaf nodes. How many swaps do the leaf nodes have to do? 0. How many leaf nodes were there? Well, in this tree, oh wait, sorry, this is not the same as the last slide. So this one is a complete binary tree, and it's not just complete, it is full. Every level is perfectly full. There are 16 nodes, 8 of them, or actually there are 15 nodes, approximately half, and over 2 of the nodes are children. I said that earlier. So about half the nodes are children. They need 0 swaps to get them into the right place. How many nodes are above the children? Well, if there are 8 child nodes, there had to be 4 parents of them. So there's n over 4 above that. They do a maximum of 1 swap each. There's a maximum of 2 nodes above that, but they do a maximum of 2 swaps each. Because remember, the fix down can proceed at most down to a leaf node. So 3 could swap with 7. Excuse me. 3 could swap with 7. 3 could swap with 16. So it did at most 2 swaps before it got all the way down to a leaf node. Now this one isn't the full example because we would have to do the fix down on each node to begin with. I went like from the middle. The root node, or the node above that, and over 16 nodes do a max of 3 swaps each. Now here with the numbers, we add everything up and there were 15 nodes and 11 swaps. That's O of n. That's pretty hand-wavy. But we could also do it, we could say, hey, let's just keep it as n. There were n over 16 nodes with 3 swaps each, right? So we've got, and just back up a little bit, we had n over 2 times 0 plus n over 4 times 1 plus n over 8 times 2 plus n over 16 times 3 plus n over 32 times 4 plus n over 64 times 5, and eventually I'll get to n over n. one node, which is the root, has log n. Now, if you take all of these and sum them up, you're going to find this sum is slightly less than n. Plus log n. Well, what's n plus log n? It's O of n. So that's why this bottom-up fix down is O of n complexity, is that we do the most swaps when we have the least nodes. Most of the nodes, half of them in fact, do 0 swaps. Half of those do at most 1 swap. Half of those do at most 2 swaps. So that's the sort of hand-wavy proof of why this is O of n complexity. All right, so that's Heapify. Heapify you need for the project. Now we're done with stuff on the project, but we still got Heapsort to go. To Heapsort, we need to Heapify. We've got to make the thing into a heap first. So once I've got it in a heap, what I'm going to do is I'm going to swap the highest priority node with the last one. So I'm going to swap the 81 and the 1, and then what I'm going to do is I'm going to say, hey, let's draw a line there. 81 is safe. It's in the right place. Let's do a fix down, but don't fix down all the way. Leave that last one alone. So we fix down of the first 8 values, and here's where we end up. So the 1 moves down until the fix down is done, but we don't fix down that 81. Then we say, okay, let's swap the 18 with the 2. Let's swap the root of the heap with the very last node. I don't care about the 2. The 2 is not important. It's that I want I want 18 to end up at index 8. So I put 18 there, and then I move my line over, and he's got the green ones. Green are good, green are safe. So then we swap. We've got 2 set aside, and we fix down, leaving the last 2 alone. And, whoops, drawing with my finger, and we end up here. So then we swap so we swap the root with index 7. Drawing with my finger again. We swap the root with index 7. We set index 7 aside, and then we fix down all but the last 3. Then we swap with index 6. We fix down to index 5. We swap. Whoops, had to clear that. We swap and we fix down the first 4. We swap with index 3 we swap with index 4 and we fix down the first 3. Swap with index 3 and fix down the first 2. And then we don't swap with index 1. Index 1's got to be in the right place. So what we do is we do repeat. So we heapify first. We do that heapify step. It's done. Then swap, fix down, swap, fix down, swap, fix down. And every fix down does a little bit less work than the one before because we've set aside those green ones that we know are in the right sorted location. So this is what Heapsort does. Heapsort says, call the heapify, make it a heap, and then repeatedly swap and fix down. And we swap and fix down everybody but index 1, because index 1, eventually, it can only be in one place. And then for this one to work, for Heapsort to work, it's important that fix down be told the size, because we're going to basically lie about the size. Every time we go through the loop, we lie and say the size of your heap is 1 smaller than it used to be. And that's how the fix down doesn't change those last elements. So like I said, this is not important for the project. I'm going to see people who do binary PQ, and it's so slow they can't figure out why it's so slow. And I say, well, what did you do in fix down? Or what did you do in the range-based constructor? They said, I did Heapsort. Well, Heapsort is n log n. We're going to prove that in a second. Heapsort is n log n. Heapify, what you have to do in the project, is O of n. Okay, so why is this log n? Well, we did this O of n stuff, right? We did this O of n stuff, was done, then we did this loop. This loop is going to run n minus 1 times. Each time that it calls fix down, it's O of log n. So that's why we've got a complexity of n log n. Is we do those repeated swap and fix downs, it's O of n log n. It requires no additional space. If we have heapify and fix down as standalone functions, where we can just say, hey, here's the array and here's the size and here's the index to fix, we can do this all in place in the original array. And this is what standard make heap does, is our heapify. Standard make heap does heapify in place. Now to heap sort, you would have to do more. Okay, so that should be just about everything for our slides today. Yep. So that's everything for today. We're a little bit over time, I know. We'll let everyone get to lunch. I'll end our video here, and I'll get some lunch, and I'll see you in Prof's hours.